Welcome back to the JavaScript Security Best Practices course on Pluralsight. I am 𝕨𝕐𝕟𝕚𝕟𝕟 and I will teach you how to write more secure JavaScript code. In the previous modules, we learned about several types of security vulnerabilities that are unique to JavaScript code. First, we saw how quirks of the dynamic type system may lead to bypass of security checks. Then, we described how dynamic code execution enabled by unsafe functions, such as eval, can lead to application and server takeover. Finally, we demonstrated how abusing the prototypal inheritance mechanism can enable a wide variety of attacks. For every class of vulnerabilities, we covered several mitigation techniques we can apply to fix them. In this module, we will focus on how to use automated testing tools to detect some of those security vulnerabilities in our own code. Automated testing is an accepted best practice in software development. In its simplest form, automated tests verify correctness of our code. They take skill and effort to write, but they are an effective way of increasing the quality of our code and preventing bugs. Tests can be used to verify other aspects of code quality: performance, scalability, robustness, as well as security. We will see how we can analyze the code for use of unsafe functions. This will help us prevent code injection attacks. Prototype pollution vulnerabilities are not easy to discover using static code analysis, and the technique we will use to prevent code injection would not work. We will use another technique, unit testing, to detect prototype pollution at runtime. We have seen how vulnerabilities can be introduced by third-party code we do not own. We will take a look at how to analyze external libraries for vulnerabilities. The Wired Brain Coffee e-commerce application had several vulnerabilities. We found them by manually reviewing the code. Automated security tests allow us to automate the process of detecting security vulnerabilities in the code. Tests will probably never be as thorough as an experienced code reviewer, but they can simplify the process. They may even be your only chance if you don't have access to engineers with security expertise. Once the code has been analyzed, we can fix the identified vulnerabilities. How do we make sure they are not introduced again by new developers, or that similar bugs are not added in new code? Running automated security tests on every code change can help a lot. Security testing at scale is a challenge. Automated security tests can help speed up the process for large code bases. They can also help achieve consistency when multiple developers or even multiple teams of developers are working on a single project. Automated tests can run really fast and can deliver just-in-time feedback about the code that is currently being worked on. Security testing can be really powerful, but there are so many types of security flaws that no single testing technique can discover all of them. The security industry has given us many great testing tools and approaches. We can classify them in three broad categories. The first category is SAST, or Static Application Security Testing. This technique is focused on analysis of code and binaries to detect known bad patterns. The second category is DAST, or Dynamic Application Security Testing. This type of security tests exercise a running application and look for suspicious responses to a variety of payloads. The third category is IAST, or Interactive Application Security Testing. This approach requires that application code is instrumented to detect malicious code behavior within the application. When the application is used or tested, the agent reports detected attacks. IAST is a new and exciting technique, but it is not nearly as popular as the first two. We will not be covering IAST in this module. Let's take a look at pros and cons of SAST and DAST applied to JavaScript code. Both SAST and DAST attempt to identify security vulnerabilities in JavaScript applications. SAST requires access to the source code to analyze. This makes it applicable to a broad range of applications, but it is not a good fit for proprietary applications where we don't have access to the internals. Working at the source code level allows static analysis tools to be very precise in locating the vulnerabilities. The tools will often pinpoint specific lines of code that need to be fixed. Dast, on the other hand, requires a running application to analyze. This makes it particularly useful for web applications. Unfortunately, it is harder to use for other types of programs, for example, command line utilities. Security vulnerabilities reported by Dast tools require manual analysis to find the root cause at the code level. Static analysis testing tools have multiple rules that describe bad coding patterns. Dynamic tools operate on sets of malicious payloads and analyze application output for predetermined signs of a successful attack. The difference has significant impact on how safe those tools actually are to use. SAS tools only read code, and there is no negative effect that they can have on live systems and customer data. Dast tools, on the other hand, send payloads to a running system. This may accidentally cause data or availability loss. That's why Dast tools should not be run against production environments if possible. Static analysis can be performed by a wide variety of tools, compilers, linters, and dedicated scanners. Dynamic analysis can be performed by our own automated tests as well as standalone scanners. Both tools rarely report the same type of issues, so you most likely need to have both in your toolbox. Linters are a fast and useful way to find bugs and simple coding mistakes. Eslint is the most popular linting tool for JavaScript. Linting and code execution start with the same step, parsing the code and building an abstract syntax tree, or AST for short. The actual analysis is performed on the AST and not on the raw code. Eslint has a modular architecture. The checks are not built directly into the tool itself, but implemented as plugins. This allowed the Eslint community to work on many useful plugins covering things such as coding style, enforcing best practices, and even simple security checks. One of the goals of linters is performance. They run quickly enough to be easily integrated into code editors, IDEs, and build scripts. In this demo, we will learn the basics of Eslint. We will install the tool and perform basic configuration steps. The core part of setting Eslint up is choosing which rules to run. We will focus on the rules that detect usage of unsafe functions, eval, and the function constructor. We will run Eslint on the original version of the Wired Brain Coffee e-commerce application and demonstrate how it allows us to detect a potential code injection attack. The first step to run Eslint is to install it. The simplest way to do it is to use the npm package manager and its npm install command. Remember about the save dev switch to indicate that Eslint is a development dependency and is not needed to run the code. The installation may take some time, so be patient. The next step is to initialize Eslint configuration for our project using the eslint init command. The configurator will ask us a few questions. We will use it to check syntax and find problems. Our project is using the CommonJS module system, and we are not using any of the currently popular front-end frameworks. The code we want to lint runs on Node.js. Let's store our configuration in JSON. The last step is installation of the latest set of rules. This may also take a little while. Eslint configuration is stored in a file called .eslintrc.json. The extends property turns on a recommended set of rules. Let's remove it for the time being to start with a clean slate. The file has a rules section where we can specify which checks we want to run. noEval catches all direct calls to eval. noImpliedEval flags uses of unsafe variants of setTimeout and setInterval. noNewFunc prevents the code from using the function constructor. All rules will generate an error. This is important if you want to break the build if any of the unsafe functions are used. Now, let's run Eslint to analyze all the JavaScript files in the lib folder. You can see that the tool raised one error and pointed directly at line 11 in the login.js file. That's right. Here's our call to the unsafe eval function. We already discussed the benefits of test automation. Now we are going to take a more detailed look on how to use unit tests to detect prototype pollution. Using unit tests to test our code for security flaws is both reliable and repeatable. Automated security tests are unambiguous, and the result does not rely on the skills and knowledge of the person performing manual code review. Commercial DAST scanners work the best for applications available through the network, such as web applications. It is difficult to use them to test those parts of our code that are not easily reachable. Using unit tests instead allows for much easier delivery of malicious payloads to the application. Unit tests also make it easier to inspect the state of the program after a malicious payload has been processed. Using unit tests, we may be able to catch errors coming from automatic conversions and loose comparisons. We may also easily check if code injection attempts were successful. We can also inspect inherited properties of objects under test to detect prototype pollution. In this demo, we will create a unit test that detects the prototype pollution vulnerability in the merge utility function. We will start by introducing and setting up Mocha, a very popular JavaScript test runner. We could achieve the same goal with any unit test framework or even without one. Mocha is simple and popular and will allow us to get rid of the boilerplate and focus on the essence of the test. Our attempt at detecting prototype pollution will consist of two phases. First, we design a malicious payload that will be very similar to the one we used in Module 4. We will inject a property to the object prototype. The second step is verification if the injected property is available as an inherited property on another unrelated object. First, we need to install Mocha using the npm package manager. Remember to pass the save dev switch to the npm install command to indicate this is a development dependency. As with Eslint, the package installation may take a while. The next step is to create a new JavaScript file for tests. There are several different conventions to organize test code, but we will keep it simple. Let's create a single file called utils.test.js in the lib folder. Let's import the function we want to test, the merge function from utils.js. We will also need to import the assert module to implement checks in our unit tests. Mocha test suites are defined using the describe function. Individual tests within them are defined using the id function. The first parameter of both functions is the name. The second parameter is a function with the body of the suite or the test. First, we use JSON parse to create the object that contains the malicious payload. The JSON document uses the special proto property to create a new property called injected with a value equal to 0. Next, we call the merge function with an empty object as the target and the payload as the source. We are almost done. Let's create an entirely new object. Now, let's check if this new object, unrelated to the payload, has the inherited property called injected. If this check passes, the function is not vulnerable. If the check fails, it is prone to prototype pollution. Let's run the test by passing the path to the utils test.js file to the Mocha test runner. We can see that the test failed, which means the merge function is vulnerable to prototype pollution. We were expecting 𝕤𝕥𝕚𝕟𝕜𝕟𝕜 to return value undefined, but we got 0 instead. This is because the property is now inherited from the modified prototype chain. We managed to write a unit test that successfully detected prototype pollution. There are plenty of security testing tools. Some support JavaScript better than others. Let's take a quick tour of free and popular commercial tools that can be used for JavaScript security testing. SAST is a very crowded market. There are both open source tools as well as established commercial vendors. We have already mentioned Eslint. It is very popular among JavaScript programmers, and using it to analyze code for simple security vulnerabilities and coding anti-patterns is an easy way to start. GitHub is a very popular development platform for both open source and commercial projects. It offers static analysis scanner as a part of its advanced security offering, including support for JavaScript. Similar capabilities are available for free for open source projects through the LGTM service, also operated by GitHub. SemGrep is an open source lightweight static analysis tool that can be run locally from the command line. It supports several different programming languages, including JavaScript. OWASP Z Attack Proxy, or ZAP for short, is the most popular open source DAST scanner. It can be used to perform dynamic analysis of JavaScript applications. DAST is also a very crowded market, and there are many alternatives to OWASP ZAP. JavaScript has a very rich third-party package ecosystem. Npm is the most popular package manager for JavaScript. Managing dependencies is an important measure to prevent security vulnerabilities introduced through external libraries. Npm Audit is a tool built directly into the package manager command line interface. It scans project dependencies for vulnerabilities. Retire.js is a vulnerability database and scanner for JavaScript. It can be called from the command line, used as a browser extension, or as a DAST plugin. Dependency Track is a comprehensive software composition analysis tool that helps manage the use of open source components in complex systems. It integrates with several vulnerability databases and has good support for JavaScript packages from NPM. Dependency Track is itself an open source project developed by OWASP. Another open source security tool is Snyk. It is a proprietary tool, but it can be used for free for open source projects. Let's take a look at how we can detect a vulnerable third-party library in our own code. In this short demo, we will analyze the dependencies of the Wired Brain Coffee application. The backend uses several open source libraries for Node.js, such as Express, and uses npm as the package manager. We will use npm audit to scan the list of dependencies of our application to detect a vulnerable Lodash version. And we will use npm to update the library to a safe version. Let's start with examining the list of libraries that our application depends on. We can do this using the npm list command. You can see that our simple application uses many different libraries and versions. It is possible that one or more of those libraries contain security vulnerabilities. We can check this using the npm audit command. You can see that the version of Lodash we used contains 8 different security vulnerabilities. 5 of them are prototype pollution bugs. We can use npm install to upgrade to the latest version of Lodash. Running npm audit confirms that we have updated Lodash from 4.17.4 to 14.17.19 and that this version has no known security vulnerabilities. In this module, we learned about the most popular security testing techniques. SAST, or Static Application Security Testing, is a technique that focuses on source code analysis. SAST tools look for known bad patterns that can introduce security vulnerabilities. DAST, or Dynamic Application Security Testing, focuses on testing the running application, usually over the network. Test tools send specially prepared payloads to the application and analyze responses to look for signs of successful attacks. IAST, or Interactive Application Security Testing, is a combination of the previous two approaches. This technique is very promising, but it is not very popular yet. We demonstrated how to use automated SAST and DAST tests to discover vulnerabilities explained in previous modules. We demonstrated how to use Eslint to prevent a code injection vulnerability. We also saw how to use unit tests to detect prototype pollution in the merge utility function. We also learned how to use Npm Audit to detect vulnerabilities introduced through third-party code.